Hello everybody, and welcome to the beginning of Chapter 7. We are looking at page 54 in the workbook here, and the topic of this chapter is cosets and Lagrange's theorem. Lagrange's theorem is one of the biggest results in group theory. It's going to give us some really useful information about what types of subgroups a group can have. And the key to getting to Lagrange's theorem is to talk about something called a coset. That's how this chapter is going to start for us. Okay, so I'd like to illustrate this concept by looking at an example. Now let's read example 1 together here. So they'd like us to consider the subgroup H equals the identity permutation 1, the permutation cycle 1, 2 of the group G equals S3. Remember that S3 is just the set of all permutations on a set of 3 elements. And we're going to define what's known as a coset right here. And let's take a look at what that is. So A times H, notice that H is a set, okay, and that's the definition of that is we're just going to take the element A and we're going to multiply it one at a time by everything that lives in our subgroup H. So this is going to be a set that we get by multiplying A through our subgroup essentially. Okay, and they'd like us to calculate this coset AH for several different values of A in our group. All right, so let's do this calculation, just see how this looks. Okay, so the first element that I'm going to choose from S3 is the identity, just because that's a nice one to start with. And the question is, what would happen if you took the identity permutation and multiplied it by both of the elements in the set H? Okay, well, if you multiply the identity by anything, you're just going to get the same elements back again. Okay, so multiplying through by the identity is just going to leave H the same as what it was before. And we're going to get the same set back again. Okay, let's pick another element in G. Okay, so how about the permutation 1, 3. That's also a permutation on 3 elements. What would happen if we multiplied 1, 3 through by our set H? Okay, and remember again that H is this set up here that I'm underlining at the top. Okay, so we're just going to take that element 1, 3 and multiply it by both of the elements in H one at a time. Okay, 1, 3 times 1, 2. And then we're going to do those multiplications. So 1, 3 times the identity permutation, that's just going to give us 1, 3 back again. And then if you do the multiplication of 1, 3 times 1, 2, and I'm saying times, but I really mean composition. This is function composition. You can check and verify that you're just going to get the 3 cycle 1, 2, 3. Okay, so there's our coset of 1, 3 times H. And we're going to keep going. Okay, there are 6 elements in the group S3, and so we're going to be multiplying all 6 of those elements by H one at a time to get our cosets. All right, so how about, let's see, I'm just going to pick another one kind of at random here. How about 2, 3? That's another element in S3. And if you take that, and again, just multiply it through by both elements in H, you're going to get 2, 3 times the identity, which is just 2, 3 for the first one. And then if you take 2, 3 times 1, 2, I'll ask you to check and verify that you get 1, 3, 2. Okay, so let's see, we've taken care of 1, 1, 3, and 2, 3. How about 1, 2 times H? Okay, so if we take 1, 2 and multiply it by the identity element, we're going to get 1, 2. And what happens if we take this 1, 2 and multiply it by the second element of H up here? If you take 1, 2 and multiply it by itself, you're going to get back to the identity. Okay. And let's see, we've got 4 down, 2 more to go. So let's see, 1, 2, 3, that's also a permutation in S3. We multiply that through by the elements of H, we're going to get 1, 2, 3 for the first one. And then 1, 2, 3 times 1, 2, you can check and verify that you're going to get 1, 3 if you do that. Okay, and 1 more to go. Okay, 1, 3, 2 times H is going to give us 1, 3, 2. And 1, 3, 2 times 1, 2 would give us 2, 3 if you check my calculations there. Okay, So S3 has 6 elements. We've gone through those elements one at a time and written down a coset for each element. And now I'd like to make some observations here. Okay, so we wrote down 6 cosets, but are those 6 cosets really all different from each other? Okay, notice, for example, that this one shows up twice. Okay, the set that contains the identity permutation in the cycle 1, 2, that appeared down here. The elements are in a different order, but as sets, they're equal to each other. Okay, so this coset that we got by taking 1, 2 times H, that's actually equal to just the subgroup H. Okay, and notice that there are other repeats. Okay, for example, the coset 1, 3H, that got repeated right here. Okay, so this one is equal to, 1, 3 times H. And then the last one, that's the same coset that we got when, let's see, which one are we missing here? Here and here. Those are also the same cosets. So this is equal to 2, 3 times H. Okay, so it's kind of interesting. There are 6 elements in S3, but we only got 3 distinct cosets. And we can draw an interesting diagram just to illustrate the behavior of these cosets. This is going to be what we call a partition. You might remember this term when you talked about equivalence relations, maybe in previous courses. Okay, so I'm going to split this into 3 pieces because we got 3 distinct cosets, and then just write down the elements in each coset. So one of our cosets contained 1 and 1, 2. The second one contained 1, 3 and 1, 2, 3. And then the third one contained 2, 3 and 1, 3, 2. Okay, those are our 3 cosets. And notice that they form a partition of S3. This diagram that we just drew contains all elements of S3, but broken down into these 3 cosets that we found. Okay, so the sets partition, S3. And we're going to see in future examples that this partitioning behavior is true of all cosets